Oops. Okay. Yeah. So just to give context, we are doing the escrow program today on Solana. First, the required crates are brought into scope using the use keyword. And then we use the entry point macro to declare the process instruction function. So this is a macro, and we are declaring the process instruction. If we want, we can quickly go through what macros do. Okay, so we use macros, what a macro is and how it works. The term macro in Rust refers to a family of features, declarative macros with macro rules, and three kinds of procedural macros. Custom macros that specify code added with a derive attribute used on structs and enums. Attribute-like macros that define custom attributes usable on any item. Function-like macros that look like function calls but operate on the token specified as an argument. Okay, let's see what are macros. Fundamentally, macros are a way of writing code that writes other code, which is known as meta programming. Okay, in Appendix C, we discuss the derive attribute, which generates an implementation of various traits for you. We have also used the println and vec macros throughout the book, right? All of these macros expand to produce more code than the code you have written manually. That means this entry point macro is actually an expansion to some other piece of code. Metaprogramming is useful for reducing the amount of code you have to write and maintain, which is also one of the roles of functions. Correct. However, macros have some additional powers that functions don't. A function's signature must declare the number and type of parameters the function has. Macros, on the other hand, can take a variable number of parameters. We can call println hello or okay with 2 arguments. Also, macros are expanded before the compiler interprets the meaning of the code. Oh, that's interesting. What does that mean? Expanded before the compiler interprets the meaning of the code. So a macro can, for example, implement a trait on a given type. A function can't, because it gets called at runtime and a trait needs to be implemented at compile time. Okay. The downside to implementing a macro instead of a function is that macro definitions are more complex than function definitions because you're writing Rust code that writes Rust code. All right. Due to this indirection, macro definitions are generally more difficult to read, understand, and maintain than function definitions. Another important difference between macros and functions is that you must define macros or bring them into scope before you call them in a file. As opposed to functions, you can define anywhere and call anywhere. Okay. You must define macros and bring them into scope before you call them. As opposed to functions, which you can define anywhere. Okay. So that's why the entry point, we have to bring it before we are actually calling it. All right. That is interesting information. There is a playlist on Rust concepts which has macros. That is our favorite playlist. Okay, let's try this one.
If you want to know how to build extremely complex front ends driven by basic concepts and principles using...
Hi guys, welcome back to Introduction to Rust. My name is Tensor. Today we're going to be looking at macros in Rust. So Rust provides a fairly powerful macro system which allows for meta programming. Macros look like functions, except they use a bang at the end, or in other words, an exclamation point. So for instance, the println statement and the vex statement are both macros. As you can see here, they end in an actual exclamation point. So any function that you've seen thus far that ends in an exclamation point is actually a macro. Instead of generating a function call, macros are expanded into source code, which then gets compiled with the rest of the program. Unlike C or other languages, Rust macros are expanded into abstract syntax trees rather than string preprocessing. And this has a number of different advantages to it.
Just give me a second. I want to create. If you already are familiar with macros and how they work in Rust, you can just continue with the next part of the tutorial. I want to ensure that this concept is clear before moving forward.
Println statement and the vex statement are both macros. As you can see here, they end in an actual exclamation point. So any function that you've seen thus far that ends in an exclamation point is actually a macro. Instead of generating a function call, macros are expanded into source code, which then gets compiled with the rest of the program. Unlike C or other languages, Rust macros are expanded into abstract syntax trees rather than string preprocessing. And this has a number of different advantages to it. All right, so to create a macro, we use this macro, ironically, called macro rules. And we have the name of the macro, followed by a set of curly braces. And then we have a unit here, followed by a what looks like a match statement. And then we have another unit here with the body of our macro. So in this case, the body of our macro just invokes the println macro with a string inside of it. It just says this is a macro. So we can just call on our macro just by calling the name of it, which in this case is a macro, followed by an exclamation point and parentheses, and then we can run it. And you can see here, predictably, it just prints out the statement that we have.
Okay, I'm just gonna say my shift is badly broken. Macro, and then call this. Narrate.
So we can just call on our macro just by calling the name of it, which in this case is a macro, followed by an exclamation point and parentheses, and then we can run it. And you can see here, predictably, it just prints out the statement that we had inside of our macro body. So you may be looking at this simple example and thinking, well, why exactly are macros useful and when should I use them? Well, typically you use macros when you don't want to repeat yourself. So there are many times inside of a program where you'll find that you're using similar functionality, and maybe you want to make it a little bit easier on yourself. So you create a macro that does it for you. Also, you can use macros to implement domain-specific languages, or DSLs. If I wanted to, I could actually write a fully working Lisp language inside of Rust using the macro system. Also, you can use macros to implement what are called Veratic interfaces. Now, Veratic interface is similar to the println statement in that it allows us to have a variable number of arguments inside of our quote-unquote function. So with the println statement in Rust, we can have essentially any number of arguments in it and it'll still run. The arguments of a macro are prefixed by a $sign. So in this case, we have our argument as E, and then we type annotate them with what is called a designator. In this case, we're using EXPR, which stands for expression. So we're saying here that this E quote unquote variable inside of our macro can be any expression. And since Rust is essentially an expression-based language, this can be virtually anything. What our macro here is doing is it's actually using two match statements. So we have a match statement here, and then we have a match statement here. So when we call this one down here where we have X and then we have the arrow for 10, this will take 10, assign it to E, and then put it inside of this println statement. When we have y here, this will take the 20 plus 30, assign it to e here, and actually print out y and then 20 plus 30 as a string. And you can see here we get our x and 10, and then we get y and 50. All right, so for our ln statement, when we
Okay, so if we send an expression in E, $E is the variable which takes in an expression, and then we can send in any expression here and then print it out. I'm intrigued to see how a Boolean expression might look like. Yeah, say X and Y, and then the first one, X, the expression, and then say X and Y, and say Y, maybe 10 greater than 20. Okay, so this should ideally return a Boolean value. Let's see. Cool. Okay, that works.
we have y here, this will take the 20 plus 30, assign it to e here, and actually print out y and then 20 plus 30 as a string. And you can see here we get our x and 10, and then we get y and 50. All right, so for our new macro here called build fn, we have a function name here, which is an ident, which stands for identifier. And identifiers are typically just function names or variable names. In this case, it's standing for a function name. So we're using our fn keyword here, and then we're putting in the variable here, which is our function name. And then we're calling a print statement, and we're stringifying the function name here so that we can pass it into our println statement here. So what is this macro doing? Well, it creates a function which we can then run, which will then call this println statement. So you can see here, we can actually run the macro, and then we can run the function that we passed into the macro. So the function just takes on the name of the whatever we've passed into this macro. So in this case, hi there.
Okay.
And then we can just run hi there by prefacing it with a pair of parentheses. And you'll see here we get you called hi there with parentheses. All right, let's look at this other example. We have an example called print.ex. It takes an E expression, and then it prints out that expression. So it stringifies.
Okay. So I think we have a fair understanding of what macros are right now. Let's go back and take a look. So the entry point macro is the one that we are calling, and this takes an argument, which is a process instruction. However, I don't know how to see this macro. Okay, I figure out a way. And the process instruction function takes 3 arguments. So this we have already gone through. It's a program ID, the accounts, because in Solana, the model is in such a way that all the information stored on accounts, and instruction data. So this specifies what exactly this program is meant to do. And then in, okay, so it's returning program result, but I think this is deprecated in the newer versions of Solana. So I think it is now this, my understanding. Yeah, okay. And then it's just calling this message macro, which is printing out the data. Yes, okay. Okay. All right. Entry points are the only, okay. Entry points are the only way to call a program. All calls go through the function declared as the entry point. Okay. So this is the function declared as the entry point, that is process instruction. So all calls will go through this. When called, a program is passed to its BPF loader, which processes the call. Different BPF loaders may require different entry points. Okay. Maybe we'll mark this as a to-do and do this a bit later. The reason for the existence of multiple BPF loaders is that in itself is a program. If updates are made to the program, a new program version has to be deployed. We can see that the BPF loader we're using requires the entry point function to take three arguments: program ID, yeah, instruction data is the data passed to the program. Finally, to understand what accounts are, we have to dive. Okay, we have already done this, so no need. Solana programs are stateless. We're familiar. If you want to store state, use accounts. Programs themselves are stored in accounts which are not executable. We already had a session on this. The way it works is that basic SOL transactions are handled by a program on Solana, the system program. Yes. Okay. This is really all about the Solana accounts model, which we have already done. So let's start. Okay. Now to finally conclude this section, create a new entry point.rs file next to lib.rs and move the lib.rs code there. Okay. Move this to here. Okay. You will have to do this for all the files we create. Inside lib.rs, only the following line should be there. Mod. Okay. Each program is processed by its BPF loader and has an entry point. Accounts are used to store states. Accounts are owned by programs. Only the account owner may debit an account and adjust its data. Okay. Instruction.rs part 1. General code structure and the beginning of the escrow program flow. Create a file instruction.rs. Next to the other two and register it inside lib.rs like you did with the entry point. To understand the new files or register it, that means something like this. Mod instruction. To understand the new file's purpose, let's look at a common way to structure a program's code and the way we will structure our program as well. Okay. Lib.rs is used for registering all the modules. Okay, that's what we're doing right now. Entry point.rs, entry point to the program. So we have the process instruction code here. Instruction.rs, which is the program API, deserializing instruction data. Okay. So whatever instruction data comes here, we'll deserialize and understand what is the data that's being passed to the program. Processor.rs will have the program logic. State.rs will have program objects. Okay, deserializing the state. And error.rs will be the program specific errors. Then we have git ignore cargo. Okay. Someone calls the entry point. The entry point forwards the arguments to the processor because that will process the instructions. Oh no, what does processor do? Program logic. Okay. Processor asks instructions.rs to decode the instruction data argument. And using the decoded data, the processor will now decide which processing function to use to process the request. The processor may use state.rs to encode state into or decode the state of an account which has been passed into the entry point. As you can see, instructions.rs defines the API of a program. While there's only one entry point, program execution can follow different paths based on the instructions that are sent to the program. Okay. All right. Just give me 1 second. I have to take a quick pause. You can continue. I will just be back. let's take a look at the different execution paths our program may take by zooming out and sketching the program flow. Remember, we have two parties, Alice and Bob. That means there are two system program accounts. Okay, let's draw this out. Because Alice and Bob want to transfer tokens, we'll make use of the token program. In the token program, to hold a token, you need a token account. Both Alice and Bob need an account for each token. Okay, so there are two system program accounts, one for Alice and one for Bob. And then there are two token program accounts, one for token X and one for token Y. Alice, I'll call our token. Okay, both Alice and Bob need an account for each token, correct? So Alice also needs one for X and Y, and Bob also needs one each for X and Y. I'll call our tokens X and token Y. Alice gets an X and a Y account, and so does Bob. Our own tokens are X and Y, but this escrow will work for any tokens in Solana. Okay, any SPL based tokens. Since escrow creation and the trade won't happen inside a single transaction, it's probably a good idea to have another account to save some escrow data. Note that this account is created for each exchange. For those of you who have experience with Solana, can you explain this part a little bit? Like, how many accounts do we need to create and based on what? Can any of you explain this part? Need a token account. Both Alice and Bob need an account for each token. So we get 4 more accounts. So, okay, 4 more. That means we already have 2 accounts and we have 4 more. And since escrow creation and the trade won't happen inside a single transaction, okay, so some escrow data. That means once the escrow is created, there is some data associated with the escrow. So there is a contract for that. Sorry, there's an account for that. Okay. Note that this account is created for each exchange. This part I don't have much clarity on. Maybe we'll just note this pointer and we can kind of discuss. Accounts. Okay. For now, our world looks like this. There is the escrow program, okay, that owns the escrow state account. And then there is the system program that owns Alice's main account and Bob's main account. And then there's a token program for which both Alice and Bob have their own accounts. Okay. How will Alice and Bob transfer ownership of X and Y to the escrow respectively? And how are their main accounts connected to their token accounts? Yes, this is a question I have. To find answers, we must briefly jump into the token program. Let's do it. Token program part 1, token ownership. The naive way one might connect Alice's main account to her token accounts is by not connecting them at all. Whenever she wants to transfer a token, she'd use the private key of the token account, right? Because it's her own account. Clearly, this would not be sustainable if Alice owned many tokens because that would require her to keep a private key for each token account. It would be much easier for Alice if she just had one private key for all her token accounts, and this is exactly how the token program does it. Okay, it assigns each token account an owner. Each token account will have an owner. Okay. Note that this token account owner attribute is not the same as the account owner. Okay. So, yeah, no problem. The account owner is an internal Solana attribute that will always be a program. The new token owner attribute is something the token program declares in the user space. It's encoded inside a token account's data in addition to other properties. Okay. So token owner has something called authority, which can be designated for each of the token accounts. Okay. And the Solana internal owner is the, okay. The existence of the authority also means that once a token account has been set up, its private key is useless. Only its authority matters. Okay. So in a token account, I guess we can have multiple tokens. I hope. Can we have multiple tokens? Need to ask this question. Only it's and the authority is going to be some other address. In our case, Alice's and Bob's main account addresses respectively. When making a token transfer, they simply have to sign the transaction with the private key of the main account. Account modifiable by owner program Lamport data, not modifiable. Key is signer, owner, executable, and debug. Okay. We can see all this when looking at a token account in the Explorer. Let's look at this. Token account, address, mint, owner, token balance is tokens. Okay. So more than one tokens are possible. All right. Okay. That question is answered now. Yes. We can see, you have probably noticed the mint field in the Explorer. This is how we know which token the account belongs to. For each token, there is one mint account that holds the token's metadata. We'll need this field later to verify that the token accounts Alice and Bob use really belong to asset X and Y. Oh, no, 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 no. I think one token account can only hold one type of token. That's why there is this mint. So for every type of token, I have to have a token account. And instead of having a private key, I'm just going to have an authority. Oh, that's still too many accounts. Okay. We'll need this field later to verify belong to neither party is making in the wrong asset. With all this in mind, we can populate our world with more information. This lot. Okay, let's see. Okay. Let's start temporary escrow state. Okay, mint X. This is the token X, let's say. Alice's belongs to, okay, Alice's token account, which is owned by Alice's system account. Then there is another account. Okay, these two are Alice's X and Y accounts, and they are owned by Alice's system accounts, and they are pointing to the particular respective token. So this is something like USDT, like mint here, this mint feature, and then maybe another one is something like USDC. And this is the same over here. Both of these system accounts are being owned by the program. For simplicity's sake, I have removed the programs and their arrows and simply colored other accounts appropriately. Once again, the owned by arrows are referring to the user space ownership, not the internal Solana account ownership. Now we know how all these accounts are connected, but we don't know yet how Alice can transfer tokens to the escrow. The only way to own units of a token is to own a token account that holds some token balance of the token referenced by the account's mint property. Hence, the escrow program will need an account to hold Alice's X tokens. One way of achieving this is to have Alice create a temporary X token account to which she transfers the X token she wants to trade. Why is this temporary account being created? Only way to own units of a token, to own a token account that holds some token balance of the token Oh, referenced by this mint. Hence, the escrow program will need an account to hold Alice's X tokens. One way of achieving this is to have Alice create a temporary X token. Okay. So here is a temporary token that this mint should refer to. What does that mean? I'll click on this mint and see. Oh, okay, just a token. Mint authority, fee authority. Okay. The next part is program derived addresses as to how Alice will transfer the ownership. Okay. So what we will do is already 7. Okay. So what we'll do is I'll do some more research on this part regarding the tokens, and I hope you're all also getting some time this week to be able to do some research, or if you're already familiar and can share some resources in Telegram as well, please do share. And once we have this part nailed down, the next thing is the program derived addresses, so we can go to that part and then finish. I think as the theory finishes, we start with the contract part as well. So we have given 2 sessions for this particular escrow contract, but if it is required, maybe we can do it in 3 sessions. But one homework for after this session is to clearly understand this token model and how the temporary accounts will function. Once we have that clarity, it will be easier for us to move on to the program derived addresses and the next part of the tutorial. Awesome. So we will stop here today and continue with the rest in the next session.